Hello! Welcome back to another exciting episode of Exploring the Universe! Today, we're going to be talking about Earth's place in space. So let's just jump right into it when we talk about things called days. While we do that, something interesting, the Earth, the thing that we are on currently, is always moving. The Earth is rotating on an axis, which is an imaginary line through the center of the Earth, starting from the South Pole, going all the way through to the North Pole. So here we have it. We have an axis. I don't know if that's the French translation, but trust me, my last name's Thibodeau. So we have this imaginary line, it's an axis, that the Earth rotates on. The axis, though, is tilted. It's not straight up and down like you might expect. It's tilted. And therefore, the Earth is rotating on its tilted axis, which is pretty cool. It's rotating on its angle. So if you think to maybe any globe you have ever seen in your whole entire life, globes are also on an axis, right? That Earth that spins around its 2 points, that axis that is spinning around is tilted. So it's kind of cool because that is an accurate representation of what we have. So the Earth, as it's rotating, it's not rotating ridiculously quickly, but it's also not rotating ridiculously slowly. It happens to rotate once every 24 hours. What? Does that number sound familiar? It should, because that's how many hours we have in a day. Nuts. It rotates towards the east. So if we're looking here, we have north, south, east, west. So it's rotating towards the east, which is why the sun appears to rise in the east, travel across the sky, and set in the west. Of course, we know that the sun is not traveling across the sky. It's in fact just the Earth rotating. And as we rotate away from the sun, it appears to set or move across the sky. But that is why it appears that the sun rises in the east, because the Earth rotates towards the east, which is crazy. And then it looks like it sets in the west because that's the last point in time in which we will see it as we continue to rotate east. So this is why we have days. Okay, so one full rotation of the Earth about its tilted axis is classified as 1 day. Awesome. We also have things called seasons. So not only does the Earth constantly rotate around its axis, but it also rotates around the sun. So this is the Earth. Tra-la-la, I'm the Earth. And I'm rotating. So if I go north, south, east, west, I'm rotating this way. It's spinning around, woo, 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 but also spinning around in a revolution or an elliptical path around the sun, which is, again, bananas. So it's rotating on its axis, but revolving around the sun. And when that Earth, or when our Earth, is revolving around the sun, at one point, we will have this axis, the North Pole, kind of tilted towards the sun, and the South Pole kind of tilted away from the sun. And at a different point, the North Pole will be tilted away, and the South Pole will be tilted towards. And if you think about it, here, when the North Pole, I'm going to put NP, it's not no problem, it's North Pole, is tilted towards the sun, this happens in June. Well, what happens in our weather in June? The weather's hot. It is nice. It is beautiful. It is summer. And when our North Pole is rotated away from the sun, that happens in December. And what happens in December? What happens to our weather? It is cold, right? So the reason that we have these seasons is because of our axis either tilted towards the sun or away from the sun, as it's rotating around, because it's continuously rotating along that axis, but that axis isn't changing as the Earth revolves. It maintains at that angle all throughout. But at one point, we'll be tilted towards, and one point we're tilted away. When we're tilted away, we have winter. When we're tilted towards, we have summer. Okay, that is why our South Pole peeps have opposite weather in our in winter and summer. So when we have our summer, it's because we're tilted towards. But notice in June, the South Pole, or SP over here, is tilted away from the sun. So in the South Pole in June, it's actually pretty cold out. That's when they get their winter. And the South Pole in December, notice that at that point, the South Pole is tilted towards the sun. And in December, their weather's pretty hot. That's their summer. So kind of cool to think about. But that is why we have our seasons. It's because of that axis. And as it's revolving around the sun, we're either tilted towards the sun to get summer or tilted away from the sun to get winter. Kind of crazy, kind of awesome, kind of wicked cool. You might be thinking, well, then why do we have spring and fall, Miss T? Like, what the heck? Well, we have summer when we're tilted towards the sun. We have winter when we're tilted away from the sun. But at some point, in spring and fall, we're not tilted towards or away. We're just kind of tilted to the side, but it doesn't really matter if I'm not pointing to the sun, I'm not pointing away from the sun. So I'm not any warmer or any colder than regular, so I have these moderate temperatures. So I'm getting my, I guess here in Winnipeg, my like 15s, my like 5s, my 10s, in that kind of range in terms of degrees Celsius, of course. And we're getting these moderate temperatures. Not too hot, not too cold, kind of the Goldilocks of it all, just right. So, that is how we get the seasons, because the revolution of the Earth around the sun is when we get those seasons based on where the axis is tilted. So, kind of wicked, awesome, cool. Something else that happens, and you might have heard the word kind of before, is we get something called an equinox and a solstice. And we're going to be talking about those right away. So the Earth's angle, or the Earth's axis is at an angle, and that angle does not change. The Earth revolves around the sun. This is why the southern hemisphere and the northern hemisphere experience different seasons at different times. All right. What else can we say? All right. At this point, there is a YouTube video that I would have shown you here in class. It's pretty cool. What I have done is I have posted all of these notes in the Files tab under Teams. If you can go ahead and check out this YouTube video after, that would be sweet. It's pretty cool. It helps better describe our seasons and better describe our days. So if you are feeling good, this would be a good video to take a peek at to really just hit those points home. Now, as promised, we're going to be talking about the equinox or the equinox and the solstice. So what an equinox is when there is equal number of hours of day as there are hours of night, right? So we're going to get an equal amount of daytime hours and an equal amount of nighttime hours. So we're going to essentially get 12 hours of sun and 12 hours of darkness. If you think about it, equinox, the first part of that word, the equi, kind of makes sense. Think of the word equals or equation, right? That means that there's an equal sign involved, and which kind of makes sense because day hours will equal night hours in an equinox. This exists everywhere on Earth at the same time. So the southern and northern hemispheres will experience their equinox simultaneously. And this happens once in the springtime. This is called the vernal equinox or the spring equinox. And this happens once in the fall. So it's either called the fall equinox or the autumnal equinox. So it happens usually in March and September, around the 22nd-ish. It's not on the 22nd every single year. It might be the 21st, might be the 23rd. It changes a little bit because every 4 years we have that leap year, and the leap year sometimes throws things off in terms of, is it actually the 22nd each day? But it's around that time period. So the reason that equinoxes occur is because these are the days that the sun rises due east, so directly above the equator. So if we're looking at the Earth, this line here is the equator, and the sun is exactly, that's the sun. I know it was poorly drawn, and I really should have drawn it in yellow. You're right, I'll redraw it. Sun, do-do-do-do, 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 do-do-do-do. I'm a sun. You're right, it needs cool shades. Cool shades. Alright. And if we're looking north, south, east, west, the sun is directly east of that equator at that particular point in time. So as the Earth rotates towards the east, then that sun is always going to be directly above the equator, providing sunlight on all parts of the Earth equally at the same time. So that's why it's experienced in the northern and southern hemispheres simultaneously. A solstice. Just like equinoxes, we will also have 2 solstices, but these don't happen in spring and fall. These happen in summer and winter. These do not happen at the same time, everywhere on Earth at the same time. So our northern hemisphere will experience opposite solstices as our southern hemisphere. So in the northern hemisphere, our summer solstice, that's the longest day of the year. The sun's going to reach the highest point in the sky. So if you're looking up, the sun will appear to be close to dead straight above you as possible, but not quite. And this happens around June 22nd. So this is when you're going to get the most daylight hours in one particular day. The winter solstice is going to then be the opposite. It's going to be the shortest day of the year. The sun rises the furthest south of east and crosses the sky in a low arc. So if this is us, we're in a little house. Yay, this is me in a little house. Or maybe I'm standing next to the house. Hi, I'm too tall to fit in the door. And this is our sky here, right? In our summer solstice, the sun rises in the east. So it starts over here. Boop, 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 boop. And in our summer solstice, the sun is going to follow a high path, right? It's going to get really, really high up to the top of the sky. In our winter solstice, it kind of appears in a flatter arc across the sky. So it's not going to go as high up. Our winter solstice in the northern hemisphere happens around December 22nd, but again, the dates may vary a little bit. In our southern hemisphere, they are flipped. So they will experience the winter solstice while we experience our summer solstice. Because when we get the most sun, they will get the least sun, and vice versa. When we have the least sun, that is because they get the most sun. So something kind of cool. All right, now we're going to start talking about stars. If you've ever looked at a night sky from the northern hemisphere, so from where we are now, and if you've watched it for a long period of time, maybe you're lying outside, picture yourself on this beautiful blanket in the middle of a field, there's not a lot of light pollution around you, you're looking up and you're like, wow, these stars just look amazing. You're lying there for a while because obviously you're admiring the beauty of it all. And the stars kind of seem to be circling one star in particular. And that one particular star is named Polaris. And Polaris is better known as the North Star. Okay, so all of the other stars seem to rotate around this one. And this North Star is located directly above our axis. So where the North Pole is, the northern star, the North Star, is located directly above that. And so as we rotate towards the east around our axis, all of the stars appear to move. They're not, it's us. We as Earth are moving. Our stars are all staying stationary, but they appear to move because we're spinning. But again, because our my North Star is directly on top of my North Pole, that one appears to stay constant because it's always right above us. Because our North Star is looking like it's never moving, it's right smack dab in the middle, all of those around them appear to rotate. We actually get a group of constellations, or a group of stars that never seem to dip below the horizon. So if you've ever looked out in the sky, you might see a couple of constellations, and you kind of see those all the time. So the Big Dipper, the Little Dipper are the ones that you probably see the most. You also might see the W of the Cassiopeia. That is another commonly known constellation. But those ones, so here's the Little Dipper. Here's the Big Dipper. And then here's Cassiopeia. Okay, so those are the three, at least that I could recognize, but probably the most commonly known in our northern hemisphere. The North Star is actually right, that's kind of dull here, is that last star of the handle of my Little Dipper. Okay, and usually the way that I find it, I don't know if this is helpful to you or not, but when you are looking at the night sky, I'm going to zoom in here. Usually the easiest constellation to find is the Big Dipper. So you have the Big Dipper here, and you can see that pretty decently. Okay. When you're looking at the Big Dipper, if you follow the path of the end of this pot here, you often can run into the start of the Little Dipper. And to find the Little Dipper, then you can go ahead and trace that until you see the North Star. Okay. And the North Star is kind of the middle of this circle of constellations here. And all of the other constellations seem to appear around it. But this particular group of constellations never seem to dip below our horizon. So we can kind of see these all year long, for the most part. I mean, of course, some days it's cloudy, sometimes, there's lots of light pollution. But for the most part, we can see these all year long. And this is called a circumpolar star cluster. Okay? So a circumpolar, so think of the word circum. That also you might think of the word circumference. So you might think of the word circumference, and if you think about the word circumference, that is the distance around a circle, right? So if we're thinking of circumpolar constellations, well, we have a circle involved, which is kind of cool. Anywho, so those, whatever constellations are found within that circle, never seem to dip below our horizon when we are in the northern hemisphere. Of course, in the southern hemisphere, they also have circumpolar star clusters, but their constellations are going to differ a little bit than what ours are in the northern hemisphere, because we're looking at different stars. Kind of cool. All right. When we are looking at the northern, or the North Star, or at Polaris, we can see Polaris at all times of the year. It's pretty cool. But if we look at it a clear night, what we would see, it doesn't seem to change position in the sky over time, but the stars around it do. So what we can do, especially if you're outside, this is what you would see. You'd see all these stars appearing to circle around Polaris. This is our North Star in the middle. And this is a picture of captured light trails of the star. And I think these light trails are absolutely insane. But this is how the stars appear to move. They appear to move in this circular path around Polaris. Almost as if they're making or outlining a circumference of a circle. Kind of insane. And if you see a time lapse of this, holy bananas, it is absolutely ridiculously awesome. One of the YouTube videos that I have here is actually going to be a time lapse of that, and it's just worth watching. It's just such a cool thing. Totally worth looking at. All right. Due to the rotation of the Earth towards the east, the stars appear to rise in the east and set in the west, just like the sun. And the sun is actually just a star, so it kind of follows the same pattern. That's just because the rotation of the Earth is rotating towards the east. So that's why we see the stars appear to rise in the east and set in the west. We see different stars in the morning than we do in the evening because we're looking at different parts of the sky, right? So if we're rotating towards the east, we're looking at a different part of the sky. And if we're looking at, what did I say to begin with? If we're looking at stars in the morning, different stars. If we're looking at the sky in the evening, different stars. We could also see different stars in different seasons. So something like Orion's Belt, that is a constellation that is also pretty well known. You could figure out Orion's Belt because you kind of have three stars that kind of form a line. That itself is the belt. I believe there's a star somewhere down here because I think this is supposed to be a sword. That's a poor sword. It kind of just looks like a cross or an axe. I don't know. But that is what Orion's Belt kind of looks like. And you can't see that all year long. You can only see that at certain times. So that's kind of neat. And that's because we are in a different place around the sun. So sometimes we are located more on one side of the sun. Okay, let's take a look. This is what I want to say. Sun. Obviously, the Earth has to be blue. Earth. And it's rotating or revolving around the sun. At nighttime, okay, so that's the axis. At nighttime, we can see these stars over here. Oh, so pretty. But in a different season, the opposite season, we can see these stars. We could always see the star that's directly above the sun, which is our northern star. I can't draw this 3D on the iPad here, but if we always look directly upward, picture an arrow coming out of your screen right now, pointing up, we will always be able to see that regardless of where we are. So, in different seasons, we could see different constellations because we're looking at different sets of stars. Alrighty, that is it for our Earth's place in space notes. I hope you have a wonderful day, and check out these YouTube videos. They're super wicked cool. Peace out, homies!